To start, we already looked at the test breakdown Tuesday, so I figured I'd include that again just to make sure. So it's all up there. Those are points. The way the point breakdown ends up coming out is roughly 50% of the points are copies from previous labs or previous lectures, exams, one of the above. Pick one.
We know what you mean.
And then the rest are kind of either new or modified versions thereof. Okay? Extended information we kind of finished up on. So nomenclature for the carboxylic acids. You are responsible for those. It's just like nomenclature for everything else, so just review that information. You're also responsible for the reactivity of carboxylic acids, which hopefully you all have a general idea of how a carboxylic acid might react, which would be probably as a Bronsted-Lowry acid. Okay? We do have lots of electrons in there. We can force that functional group to act as a base, but it's fairly rare. And it could potentially act as an electrophile as well around that carbon. Okay? But for the most part, we're really looking at that hydrogen being a Bronsted-Lowry acid. Okay? The other big thing that I want to mention as a review, because we didn't talk a whole lot about it when it actually showed up, which was chapter 10, the reactivity of uramines, which is going to be a larger portion of what we're talking about today. So we've got an amine functional group. What's our primary reactivity from amines so far? We're looking at them primarily acting as Bronsted-Lowry bases, and we're going to look at them acting as a nucleophile today. Okay? Another thing that if you want to review it, you can. I don't know the exact chapter, but the carbohydrate chapter. It's more stuff that you'd see in biochemistry, so it's not as big of a deal, but I wanted to mention it because a lot of that carbohydrate chemistry is the carbonyl chapter. Okay? And particular concern dealing with oxygens is nucleophiles. Okay, so you're forming what they typically refer to as alpha and beta anomeric carbons, which is ultimately just another way of saying acetals and the products that are formed in the formation of those acetals. Okay, so we'll look a little bit closer at that when we go back to the oxygen reactivity. Questions about any of that so far? Okay. When we looked at chapter 13 with our carbonyls, you need to know your nomenclature for your ketones. In general, your reactivity of carbonyls. Okay, all of your functional groups, you're responsible for knowing the general reactivity. So if we've got our carbonyl, what chemistry do we have? Carbonyl chemistry, fair enough. That carbon can act as... It's an electrophile because it's got an electronegative oxygen attached to it, pulling the electron density away. So that carbon is partially positive, meaning it can act as an electrophile. It can also act as a Lewis acid. Would it work to call it a Bronsted acid? No, why not? No hydrogen. What does our oxygen act as? We get Lewis base, we get nucleophile, and we also get Bronsted base. Okay? All possibilities. When we looked over the reactivity of our carbonyls, we were primarily concerned with the reactivity of the carbon as an electrophile, because oxygen is highly electronegative. It doesn't really want to share those electrons. We can force it to go out and do that, but it's fairly a temporary reaction. So our carbon is going to be a much more permanent reactive position to go for. So what we can do is look at the reactivity of nucleophiles with our carbonyl. Okay, so there were three types of nucleophiles. We could have our carbon nucleophile, nitrogens, or oxygens. If we had a carbon nucleophile, we're looking at Grignards. Nitrogen is the imine, which we'll look at in a second, and oxygen are your acetals and hemiacetals. Okay, so nucleophile, where nitrogen is our nucleophile. Okay, not sure how much I like having everything drawn up there, but let's go through and look at our reactivity for our nitrogen again. What did we say nitrogens can act as? They're pretty good Bronsted-Lowry bases. They also supply electrons, so they could also act as nucleophiles. Okay? And that's what we're going to be looking at when we look at nitrogens reacting with carbonyls. Okay? Just like with our acetals having oxygen act as a nucleophile, our reaction can be either acid catalyzed or base catalyzed. Okay? If we move into the base catalysis, we end up bringing in strong bases that can do all sorts of other weird chemistry. So we typically run with acid catalysis. Okay? So let's go ahead and take a look at that first step and try and decide what's going to happen. So among those three species there, we've got the carbonyl, we've got our amine in that nitrogen, and we have H3O+. Which of those are you most concerned about? We pull a face test. H3O+, because
It's an acid.
it's charged. Okay? That charge isn't a good thing. To fix that, we can try and pull off that hydrogen. So we have an acidic hydrogen. What do we want to stabilize that acidic hydrogen? A base. We need an electron source. Okay? This is again one of the reasons why this chemistry becomes very irritating. If we go back to our two options, we've got oxygen and nitrogen as electron sources. Both of those have lone pairs. Which one is more likely to donate its electrons to that hydrogen?
Oxygen.
The nitrogen. Why the nitrogen? It's less electronegative. We would expect that nitrogen to pick up the hydrogen in preference. What's the problem with that? Not even that. Nitrogen needs to be a nucleophile in this reaction. To be a nucleophile, what does it need to have? Electrons. Okay? If we take those electrons and we react it with the acid, can it act as a nucleophile? No. So we lose that reactivity. Okay? So why do we end up having the oxygen take the electrons? Okay? This is not a fun, happy answer, but that ends up being what happens. Okay, so why does that happen? We're in a solution where we've got lots of acids and bases floating around. Lots of different things can occur. One of the biggest things to note in each of these reactions is the type of arrow used in each of these steps. What type of arrow is that? It's an equilibrium reaction. We're getting all sorts of different reactions all happening at the same time, progressing some in a direction that we want, some in a direction that we don't want. Okay? If we have the nitrogen react with that acid, that is a perfectly valid step, except that doesn't take us to our final product. How do we know the final product was actually formed? Well, somebody mixed these reagents together, and at the end of the day, they isolated and they found out that what they had, what they found at the end of the day was the product down at the bottom. For that to be the product, the nitrogen has to act as a nucleophile. So even though that nitrogen has that base capabilities, we are forced into the situation of saying that that is likely not what actually occurred. Okay? So what ends up being our intermediate? What happens after that first step? We show any arrows to the nitrogen? No. So what happens to it? Stays absolutely the same, so we can draw that in there. What happened to our carbonyl? Nothing happened to the carbonyl, but that oxygen picked up a hydrogen. What charge is that oxygen now? Positive. Does oxygen want to be positive? No. So what happens? It's going to want to try and get electrons from somewhere. Where's a nice place to get that? It could get it from the pi bond. If it gets it from the pi bond, what charge builds on that carbon? Positive charge. That carbon lost electrons. Okay, making that carbon very electrophilic. Okay, do we have a source of electrons nearby? Say from our nitrogen. So our nitrogen can share its electrons with that carbon, and we end up producing the next species. Okay? You'll notice you get all sorts of weird structures all over the place. We've got some charge in there, which isn't particularly nice. So we're going to try and fix that structure as best as possible. What's the most unstable thing about that structure right now? Positive nitrogen. So what do we need to do to make that nitrogen happy? It needs electrons. We can't bring in electrons from an outside source. Why not? It's already got its octet satisfied. We cannot exceed that octet. So we have to find electrons near that nitrogen. So we have to look to the carbon and hydrogen bonds near it. Which of those bonds is going to be the easiest to break? Probably the hydrogen. Why? Lowest electronegativity. Okay, so we're seeing the biggest difference between those. Our ideal situation is going to be to pull the electrons away from that hydrogen. Okay, how do we know that's what happens? Well, we could cheat and look at the product of that step, and what's the result? Okay, the only thing that changed was that hydrogen's no longer there. So we took the electrons away from that hydrogen. If we wanted to balance it out, we could add in the H+. Okay? So now what we've got to do is try and evaluate what things are going on. Is that structure stable? So now that we're at our, what is that, third intermediate? Okay, no charges, but is it stable? What's special or problematic about that carbon? Partially positive because two electronegative elements attached to it. Okay, so what we want to try and do is help that process out. So what we can do is say, okay, I need to start to find ways that I can get that carbon electrons. Okay, so again, what we're going to do is take the electrons on our oxygen. We're going to share those with a hydrogen to form our next product. Okay, why do we end up going through this? What have we formed out there? Water, which is a fantastic leaving group. Okay, so what can happen at this point? That oxygen wants electrons. Where do we have electrons? From our carbon. We can take the electrons away. Let's see, which way did I do this? Okay, let's draw out our net result. See if I can draw it out. What happened to our carbon? It's now positively charged. Do I have anything that could stabilize that positively charged nitrogen, or sorry, carbon? Say electrons nearby. Say on that nitrogen. We can push those electrons in to stabilize and form our double bond. What charge would that nitrogen then build? Positive charge. Nitrogen doesn't really want to be positive, so what can happen? It can take the electrons away from the hydrogen. Sorry, it's a double-headed arrow. You can have a base such as water or something else, a weak base come through, and what we end up forming is our final product. This structure is referred to as an imine. What we're looking at is a nitrogen surrounded by carbons where it's doubly bonded to one of those carbons. We've got an imine. Okay? This type of reaction is one of the most important in biochemistry. You're seeing this reaction happen on multiple levels at multiple times. The nitrogen source, when we're looking at biochemistry, is typically coming from an amino acid side chain. Because you're in biochemistry, what amino acid is that? With a nitrogen at the end? Glutamine? I don't like glutamine. That one's got the carbonyl out there too, doesn't it? Lysine. One of your amino acids has a nitrogen on it. I can't remember which one it is. Okay. A lot of the biological structures or biological compounds floating around, your different vitamins, minerals, a lot of them have carbonyls. If you take a look at carbohydrates have a lot of carbonyl chemistry in them. And that's primarily because they're all reversible reactions. Okay, so if we go through and look at a biochemistry reaction, we want to be able to reverse it. Because if it's not reversible, we're now stuck. Okay, we can't progress anywhere from that. So almost all reactions in biochemistry are reversible in some fashion or another. And biology forces the chemistry in certain directions. Okay, by adding enzymes or doing concentration gradients. Okay? So this mechanism is incredibly important. There's a lot of different pieces and things working around with it. I don't expect you to get the exact order of each of these things nailed down because that order is questionable. Okay? Depending on when you get a hydrogen added or subtracted, you're getting all sorts of protonation, deprotonations. So what you should be able to do is work through your steps and come up with reasons that explain why you're moving to different parts. Okay? Kind of makes sense? Okay? And as long as you can put down a reasonable mechanism, I'm fine with that. Yes?
Where did methyl group come into play on the last one that wasn't there before? And the amine is another, oh, never mind, it's just rotated isolate.
Okay. Okay. Questions about this mechanism? Okay. I will go through and type this all up so it looks neat, as opposed to having to make you filter through all these notes as well. So you can make sure that you understand that and follow all those individual steps. Okay. We talked about carbons acting as nucleophiles. We did that on Tuesday. When we get carbons acting as nucleophiles, there's two primary groups where we can get nucleophilic carbons. We can get nucleophilic carbons from, which everybody seemed to remember, I guess because I've asked it too many times, triple bonds. Okay, that acetylene group is relatively acidic, so I can react acetylene with a strong base like sodium amide. I can pull off that hydrogen, and I'm left with a lone pair on that triple bond carbon. That can now react as a nucleophile. So that's one source of negative or carbonyls, nucleophilic carbons. Our other source was moving into Grignard reagents, and that's where we start with an alkyl halide. The most common one is bromobenzene. Okay, but it can be any alkyl halide. I can react that with magnesium metal. Magnesium metal comes in with 2 electrons, and in the process it intercalates into that bond. Pretty sure that's the wrong usage of intercalate, but it's good enough.
I thought you were just making up.
It is an actual word. Sits in between there. We end up with an ionic compound. Magnesium holds a +2 charge. For this structure to remain neutral, the carbon must be negative. We've now generated a nucleophilic carbon. That carbon can now react with carbonyls, and we end up generating an intermediate referred to as the alkoxide, which I'll draw out in just a second. We can then follow that up with an acid workup, H3O+, to give us an alcohol. Okay, so if we take the Grignard reagent as shown, and we react it with a ketone. Okay, our very first step is going to be our Grignard coming in with that negative charge, reacting. The electrons, or we form too many bonds to that carbon, so we push the electrons up onto the oxygen. The oxygen then becomes what charge? Negatively charged. We'll show in our Grignard now, or no longer a Grignard. We then follow that up with a step 2, okay, which is why it's shown broken down like that before, with the H3O+, which can then go through and protonate the alkoxide intermediate to form our alcohol. Why do we call it an alkoxide? Well, the alk stands for carbon-containing structure, so there's our alk, and oxide stands for RO-. Okay?
Supposed to be separate, or are they supposed to be?
Oh, fine. I'll fix that. That's fat fingers. Okay? I prefer the term fat.
What happened to your little pen?
I lost it.
You're so excited about it.
Yeah. I thought it was a lot cooler when I actually had it. Or didn't think it was cool when I had it, and then I had to start writing with my hand again, and it sucks. Okay, so that is your standard Grignard reaction. One of the issues with forming a negatively charged species, though. if we've got a negatively charged either acetylene or our bromide here, if we have a source of electrons, it can act as a nucleophile. What else can it act as? Lewis base. What else? We get a Bronsted base. Of the chemistries possible, Bronsted acid-base chemistry is a lot easier, quicker, because you're looking at the transfer of a hydrogen atom. Whereas if we look at nucleophile or Lewis base chemistry, you're looking at the transfer of relatively large groups. Okay, we've got a carbon with several other things attached to it, or our negative charge with the benzene ring attached to it. Okay, there's a lot of things having to move around in that chemistry, which means that chemistry ends up becoming a little bit more difficult. So when it comes to Grignards, because that negatively charged carbon is so reactive, we have to be very, very careful with what we expose it to. Okay? So one of the biggest issues is the presence of any kind of acid. Most commonly found in a solvent, primarily something like an alcohol. So if we look at the alcohol functional group, what's the reactivity of that hydrogen at the end? It's relatively acidic. When we put it in the presence of an extremely strong, negatively charged Grignard reagent, instead of doing any nucleophile chemistry, we end up doing acid-base chemistry. What happens to my Grignard reagent? Becomes benzene, and then I get a deprotonated alcohol left over. Okay, so we end up quenching the Grignard reagent. It no longer acts as a nucleophile, and that ruins our reaction. Okay, where this becomes increasingly tricky is, let's say instead of having an alcohol, we drew something along these lines. Because most students look at this and they say, oh, carbonyl. What's the carbonyl chemistry? Reacts with Grignard reagents. Oh, I get a Grignard nucleophilic attack. Except, what do we have on the outside? We've got that reactive hydrogen. We end up doing an acid-base reaction instead of the nucleophile, carbonyl chemistry. Okay? Does that make sense? Get the idea of what's happening with those? Okay. We then had oxygen reacting with carbonyls. As far as those compositions, sorry I didn't get time to put structures in here. You get your acetals, hemiacetals, and as far as you guys are concerned, acetal, hemiacetal, or not applicable. It's not any of the above. Or a hydrate, which we didn't directly talk about, but I'll show it here in a second. So we can start with a carbonyl. And if we're going to have it react with an alcohol, say let's do OH first. That oxygen can act as a nucleophile, and we end up with a first step. And let's color code this. Here, the oxygen attacks our carbonyl, and it adds to our double bond, and what we end up getting is the hemiacetal intermediate. Okay? If you want to remember it, hemi means you've got a hydrogen on one of those oxygens. Okay? This reaction, or this system, can react a second time with another equivalent of our alcohol.
Can you say that again? What hemi means?
We'll come back to hemi in a second. We'll get to a better definition for it. It can react a second time with another molecule of our alcohol. So we still have our OR, and we'll end up putting on another one. Okay. What we've got here is the acetal. In the case of the acetal, what we're looking at is our two oxygens are attached to carbons all the way around. So if we could only look at, see how well you guys remember your functional groups. Only look at that half, what functional group is that? No. and oxygen sandwiched by carbons?
Acid?
Ether. What's on the other side? An ether. Okay. So we can go through and look at our acetal as being a composition of two ethers centered around the same carbon. Okay, so that's our acetal. The hemiacetal, hemi just means part way. So as we move from a carbonyl to our acetal, we have to stop part way at the hemiacetal. Okay, so the only mnemonic device I could think of was if you take a look at your structure and you find a carbon that is bound to two oxygens, evaluate the next atom out. If it's hydrogen and carbon, you're looking at a hemiacetal. If it's carbon and carbon, you're looking at the full acetal. Okay? The last thing that we didn't directly mention, but let's say instead of adding the alcohol, we added water, we would end up with this structure. Whoops, it's a bit sloppy. Is this an acetal? No. Okay, we don't have the two ethers on that structure. Is it a hemiacetal? Well, for the hemi, I needed at least one carbon on one of those oxygens. It's not a hemiacetal. What do we end up calling this one? What did we add to that structure, to our carbonyl?
Hydrogen.
We added an oxygen bound to a hydrogen, so we added that OH. What else did we add to that? What other bond changed there? You added the other H. If we take off H and OH and we put them together, what do we have? Water, or hydra. So we've hydrated our carbonyl by adding water to it. Okay? What you're going to be responsible for is labeling these acetal, hemiacetal versus not applicable. Don't worry about the hydrate portion. So you need to be able to find the carbonyl or your electrophile within an individual structure. You need to be able to identify what the alcohol was within that structure too, or your nucleophile. Okay, so it's a question of going back and looking at whatever structure you've got, and since we've got them here, let's go ahead and do it. Okay, we want to mark and identify our bonds that were formed in this reaction. So we could go through and say, where's our weakest bond in the case of our acetal here?
Central carbon.
Around our central carbon, which bond around the central carbon? Either of the oxygens. Why do we not evaluate? Sorry, I didn't mean to erase all of that. Say an external bond between the oxygen and the R group out there. Why is that one not one of the weaker bonds?
Because it only has one.
Only has one oxygen on it, which means that carbon, our R group carbon out there, okay, isn't quite as positive as our carbon in the middle, because the carbon in the middle has two oxygens. Okay? So if we're going to try and break this apart to find out what our alcohol was, our ORs come off as our alcohols. We need to replace those oxygen bonds. And in the process of replacing them, we have to bring in a new oxygen. There are two oxygen bonds that we just got rid of to make the carbonyl. So it's a question of finding that position and splitting it as best you can. Okay, one of the things you'll notice with the homework that can make this trickier, when I write out an R group, what can an R group be? Anything. So what if I did this? How many species made that acetal? How many compounds went into that acetal? Two. We break the weakest bonds, which is those two. We can form our carbonyl, so there's our carbonyl compound. What happens with our alcohol? Our alcohol happens to be a diol. It has two alcohols on the same compound. Okay? So try to ignore what things are attached outwards. Okay? Don't stress too much about those. Don't change them in the process of running the reaction, but don't immediately assume that something drastically different has occurred. Okay? It's again trying to find those patterns as best you can. Okay? And then just like with the imine chemistry, when it comes to the mechanism with this, I'm really focusing on feasibility. Does your mechanism make sense? What things are being attacked? How many times are you showing arrows? Okay? You'll notice if we go back to that mechanism. Was it the last slide? 2 slides ago. How many steps do we have in there? 1 step? Lots of steps. Lots of steps. If you tried to show all of the curved arrows in one individual step, that looks like a giant mess. Okay? And what you're trying to say is that everything happens instantly. Okay? That's not very likely, not very feasible. Okay? Does that make sense? So try to break up each of your individual steps, and as long as it's not something drastically wrong, I'll accept credit for it. Okay? At this point, the idea is to see what you can build from. Okay? Copied this over from our oxygen with a carbonyl. What kind of catalyst are we using in this case? Are we under acidic conditions or basic conditions? How do you know it's basic? We see lots of anions, lots of electron donors. Electron donors are Bronsted bases. Okay, so we're under basic conditions here. So again, it's understanding what conditions we're in, how those conditions reflect the overall structure of each of those compounds. Okay? One of the last things that we looked at, just because this was interesting, we mentioned this. Why is that last step not likely? What type of mechanism are we likely undergoing here? It's a substitution, and how many steps are happening in that last substitution? It's only 1 step, which would mean we're looking at the SN2 mechanism. Under SN2 conditions, our primary concern is steric hindrance. So we want as few things as possible around our leaving group. Well, carbon, carbon, and oxygen, that's an awful lot of electron density. There's a lot of steric blocking in that reaction. So this last step under the base catalysis doesn't make a lot of sense. Okay? Does that make sense? Okay. The weird chemistry of our carbonyls is that that carbonyl in location, or in its location, can actually make some hydrogens acidic. Okay, so what we're looking at is, if we go ahead and put that carbon in there, our central carbon, we said, could act as an electrophile. So it wants electrons. So we did most of our reactions by concerning ourselves with nucleophiles reacting with that. Okay? But is there another source of electrons nearby? Say perhaps the next carbon. That carbon starts to lose electrons. Is it really happy about losing electrons? No. So what does it do? It grabs electrons from its next available source. Where's the easiest next available source? From that hydrogen. So we can take those electrons and pull them off to form a double bond, push that up, and what we end up forming is what's commonly referred to as the keto-enol tautomerization. Okay. Enol, because we have an alkene, and then that functional group up there looks very similar to, let's say if we added a hydrogen, an alcohol. So we've got the enol. I'm pretty sure that second E isn't in there. Maybe it is, I don't know. Okay? So being aware that sometimes we can force that hydrogen to be acidic enough to be pulled off. Okay? So you can get some weird and interesting chemistry there. Not to oversell it, but the chemistry is so fun that they even named it after cool people. Like me. You can get Michael reactions, actually, when dealing with carbonyl chemistry in this fashion. Okay? Also commonly used in biochemistry, you do take advantage of this kind of isomerism. I just want you to be aware of it. Yeah. Questions about your keto-enol tautomerization?
So an enol is just a negatively charged hydrogen.
It is.
Or that species right there.
This species is the enol. Yeah. So we're finally done with chapter 13. So working backwards, I've got these in reverse chronological order. With chapter 9, this is with our aromatic rings, or our arines. Our primary concern with these was aromaticity at first. Aromatic rings tended to be very, very stable, which tends to be a good thing, and that makes them less reactive. Okay, so we need to know what qualifies for making something aromatic. Those rules were established by a man named Huckel. I think it's a man. I'm actually not sure. We'll say a she-man. That way we can cover all the bases. Or a person. It might have been. It could have been an alien, though. So.
That's probably doubtful.
Oh, okay. So Huckel came up with these rules for aromaticity. So he was able to look at a variety of different structures and evaluated how stable they were or how reactive they were. And what he ended up finding out was that first off, to be aromatic, the structure has to be cyclic. So we have to have a circular compound. We have to have p-like orbitals on each atom, which ultimately means, or where our big comparison was, is we'd be looking for sp2 atoms. Probably even see sp in there, but our biggest focus is on sp2. If we had an sp3 atom, that sp3 atom needed to have a lone pair. Because with that lone pair, bless you, it could donate electrons in through resonance, and in the process of doing resonance, if you evaluate the hybridization of that atom, you'll find out if it does that resonance, it becomes sp2. Okay? We got rid of the approximately planar rule. You don't have to worry about that. And then there's the electron count. It has to have 2, 6, 10, or 14 pi electrons. You can either memorize 2, 6, 10, 14, or realize the pattern, and that's the 4n plus 2 rule, where n is any integer. Okay, so if n was 0, 4 times 0 plus 2, 2. If n was 1, 6. Okay, 10, 14, and it continues on extending wise. That was eloquent. Okay. The other thing we had, we're dealing with our electrophiles. Okay. There were 6 primary electrophiles when it came with EAS reactions. So our electrophilic aromatic substitution. On the right-hand side, I tried to show in larger letters and now boxed in, being the actual electrophile that's getting used in that reaction. So in the case of the first 2, it's fairly obvious-ish. We're looking at substituting in a chlorine. In case 2, we're looking at an R group. So the R group would be any carbon-containing thing is what we're focused on there. In the last case, where's our electrophile? Ends up being the carbon, which is not where our positive charge is located. Why is the carbon our electrophile? How many electrons are around the oxygen? Sorry.
Not in bonds?
How many electrons are around that oxygen? Total. It's got its octet. It cannot accept any more electrons. Okay? If we look at the carbon, we could push electrons into that, and we could break a bond, pushing electrons out onto the oxygen, which is where they would like to be anyway. Okay, so our electrophile ends up being that carbon. Okay, how we form each of these reagents or these chemicals, our electrophiles, is what's given on the far left, and in between we've got the intermediates. You should be able to draw mechanistic arrows connecting all the dots, that kind of fun stuff. Okay, that previous slide was looking at our electrophiles coming from Lewis acids. We could also make electrophiles by reacting with Bronsted-Lowry acids. So the most common one, or my favorite one, which was the one up at the top, you react nitric acid with sulfuric acid, and we can form the nitronium ion. There's our electrophile at the very end. Okay? The less commonly questioned one, but you could get credit for this on exam 3, was using sulfuric acid and an aromatic ring. Sorry. Oh my gosh. What are you doing, slides? You could generate the sulfate as an electrophile, and you could do what's referred to as a sulfonation by adding a sulfate to the ring. Okay, and in the last case, we can form a carbon electrophile by reacting an alkene with a strong acid. This acid is very, very special, though. What is special about this acid? We balance the reaction. What's the other product? Sulfate. The issue with sulfate, it's got a lot of resonance, which means what about the negative charge?
Stable.
Very, very stable, meaning it's not nucleophilic. So if I add an alkene with sulfuric acid, the hydrogen protonates, I form my cation intermediate, and the sulfate cannot form that bond. Okay? If I added something like HCl, what's the issue with HCl? I now form Cl minus. Cl minus, or chloride, all of your halogens are reasonable nucleophiles. The nucleophile attacks and we get the full substitution, or sorry, the full addition reaction. Okay? So it's realizing what those individual pieces are doing. Why does certain chemistry happen over others? Okay, questions about that? The next part, unfortunately, I didn't have the resonance structures all drawn out. I had them just by hand. So I kind of tried to abbreviate it as best I could with this. And we should kind of ignore that title. This is just the summary of our nucleophiles. Of our aromatic nucleophiles on how we can change them. Okay? So what we can go through and do is evaluate the reactivity in each of our structures. And what we can end up doing is changing from our benzene, which has just hydrogens attached to it. So if we compare, we go up to hydrogen. Here we add an atom X. Atom X in this notation means any group. It can be anything. Okay? Or we could go to atom X down below, and in that case, what's happened? It looks slightly different. Okay? So the patterns that we notice, if we start up top, if atom X has more electrons than a hydrogen atom, okay, typically you're looking for lone pairs. Lone pairs are your big red flag for having more electrons. Okay? If you've got those lone pairs, those can donate into the ring. So our reaction ends up going faster. We make our nucleophile more nucleophilic. So atom X would act as an activator, and it would direct the electrophile to the para or ortho positions. Okay, if we looked at the bottom case, if atom X had less electrons than a hydrogen atom, remember we're looking at a hydrogen atom which has technically one electron. The only way we can get less electrons is by putting a positive charge on that atom. So at any point, if I can draw resonance or look at electronegativity effects, put a positive charge on the atom immediately attached to the ring, that atom is going to draw electrons away from the ring. Well, if the ring loses electrons, it loses its ability to act as a nucleophile, and it ends up deactivating the ring. Okay, so our reaction goes slower. Also, as a repercussion of that electron withdrawal, we get meta-directing. Okay, everybody remember ortho, meta, para? We need to review those. Okay. The one exception to these two very nice, neat rules is if atom X is a halogen. Okay. In the case of atom X being a halogen, it is a deactivator based on the electron withdrawing effects of the halogens. Okay, they're all fairly electronegative. But it directs to the para and ortho positions because of the electron density on that halogen. Okay? Those electrons overlap within the ring and allow the para and ortho positions to have a little bit more electron density. That's where our electrophile adds. Okay? Questions about EAS or anything with Chapter 9? Okay. Chapter 8 was our alcohols. I've kind of just grouped it into pretty much all the other chapters, both in our alkene material and in our substitution material, because ultimately that's all what was really discussed in that material. Okay, so you get reactions of, which are typically your substitution and elimination. We do have the extra, I guess if you want to call it, a benefit of dealing with oxidation. So we can oxidize our alcohols up to aldehydes or carboxylic acids or ketones. And then we can also look at the possible reactions as far as making them. Okay? So to make them, we're focused on substitution reactions or addition reactions. Okay? I don't remember if I actually put examples in here. Nope, I didn't. Do you guys have any immediate questions about the alcohol chapter? Okay. Remember, when it comes to alcohols, you've got lots of sites of reactivity. That functional group is just obnoxious because the oxygen can act as an electron donor. The hydrogen now lost electrons due to the oxygen pulling electrons away. So the hydrogen acts as an acid. And then the carbon also has the same effect as the hydrogen. It's losing electrons to the oxygen, so it can then act as an electrophile. So there's lots of reactivity when we come to the alcohol. Okay, we then can jump back to chapters 4 and 5 with the alkenes. Chapter 4 was primarily nomenclature, and then looking at cis-trans isomerism, okay, or E and Z nomenclature. Okay, as far as reactions, we got a lot of addition reactions, which is pretty much the only reaction that they can do. Okay, so we can have our alkenes react by adding something to the double bond. Okay? The other option is making them. The only way we can really make those is by doing elimination type reactions. Okay? There's lots of reactivity in our alkenes, so you could potentially see a lot of questions showing up through there. Okay? As far as assigning your cis and trans, hopefully you guys remember all the patterns that we established for this, so we can cut the double bond perpendicular to the double bond, so we can cut it in half that direction. We can assign priorities to each half if possible. If we can't assign priorities, like in this case, hydrogen versus hydrogen, no difference. There's nothing to star. That structure cannot act as cis or trans. We get no isomerism. Okay? The other fun, goofy exception that we could look at is if we look at the cyclopentane down at the bottom, we can go through and cut that double bond in half and go through and evaluate the pieces attached to it. So we evaluate each half. Sometimes it's helpful to add the implied hydrogens. Hydrogen versus carbon. Which one's higher priority? Our carbon, so we can star that. We go to the other side, hydrogen versus carbon. Carbon. We could then go through and say that the relationship in that structure is that our double bond is cis. We could take it a step further and we could say it is Z. Okay?
Cis-trans is sometimes right, but if you use E and Z...
Yes. E and Z is always correct. Cis and trans is not always correct. Cis and trans technically only refers to the relationship between two atoms or two groups. It does not refer to more than that. So when you go through to name things, if you say E and Z, or even move to R and S, those will always be correct. Cis and trans is got some exceptions or is limited to certain situations. Okay. The last thing that hopefully everybody has seen now from exam 3, does this structure, our cyclopentene, exhibit cis-trans isomerism? We do have the cis conformation there, but it is physically impossible to make the trans. If it's impossible to make it, we can't have the isomerism. We cannot switch between cis and trans. Okay? So your cyclic structures are locked in the cis conformation. You can only move them into the trans when you have 8 or more carbons. Okay? So as far as you are concerned, there's no cis-trans isomerism with cycloalkenes. Oh, and there's our rules on the E and Z. So adding those in. Come on. Alkenes is Bronsted bases, so we can react them with strong acids. So we can get the hydrogen to add to that double bond. Okay, we talked about this a while ago, so we can cut this in kind of half here. That hydrogen can go to either of those two positions. So when we look at the mechanism, we're taking the electrons from that pi bond and sharing them with the hydrogen. I'm going to balance that out and shift that over too. Now trying to decide where that new bond is. Okay, we're sharing electrons, so we're forming a bond. We can't have a bond between a hydrogen atom and a bond. Okay, that doesn't make sense. Okay, so that our bond connecting the hydrogen has to be attached to one of the carbons. So it's going to be either end of that double bond. Okay, so then we'd have to decide, is there a difference between those two carbons? Well, is there? Yes. So depending on the situation, you might end up drawing out both possible products. So in one case, we attached the hydrogen to the end. In the other case, we attached it on the inside. What's the difference between those two possible products?
One is secondary, one is primary.
We can look at where our positive charge is located. In one case, that positive charge is a primary carbocation. In the other case, it's secondary. Which is a more stable place for a cation? Secondary, which means the secondary product is going to form. Our primary does not, which means our favored product puts the bromine in the middle there. Okay, this was commonly referred to as Markovnikovs. Was it Markovnikovs?
I thought it was Hoffman's, I think.
I don't remember the names.
Oh, Hoffman is the rich get richer.
No, this is a rich gets richer. I think it's Markovnikov. Okay, so the rich get richer. Our hydrogen counts as money. We're going to put the hydrogen wherever there's the most hydrogens already. So if we go back to our starting material, we look at those two carbons again. Which of those two carbons has the most hydrogens? Our rightmost one, that's where the hydrogen needs to go. We translate to the top structure. Okay. The other reactivity we could see would be reacting with water and adding HOH, so adding H2O across the double bond. Water is not active enough in this reaction, so what we end up having to do is add an acid catalyst. We need that acid to react with the base of our alkene. Okay, the alkene is acting as a Bronsted base, but it's not a very strong one. Okay, so we have to add a strong acid to facilitate that reaction. Okay, you'll notice as soon as we have that acid, we're still looking at our Markovnikov rule. Okay, questions about alkenes as Bronsted bases? We can also look at alkenes as nucleophiles. This one was a little bit less obvious to see it acting as a nucleophile, but it is indeed. We're taking the electrons from the double bond, reacting with that bromine, which may appear to have a bunch of electrons, but we can polarize it, making that bromine very, very positive. We can get the bromine adding to that structure. Okay? Bromine being large enough will stabilize the carbocation intermediate by forming what's referred to as the bromonium ion. So we've got a cyclic bromine ring, which I tried to show from the side angle there so we can see it a little bit cleaner. Okay. At that point, we're still unstable. The bromine doesn't want to be positive, so it's going to break one of those bonds, and in the process, that puts what charge on, say, that carbon now? Positive, making that carbon act as an electrophile. So what do I need to find? Good call. Really going for a nucleophile, but yes, that works. So we can go through and look within the rest of our reaction. In this case, we've got the bromide. The bromide can act as our nucleophile and attack that positive carbon, and we get our ring opening. You'll notice we have stereochemistry in the product. Okay, so you are responsible for knowing how that mechanism works to produce where those bromines add to the double bond. Okay.
Adds an SN2 reaction.
You can't quite call this SN1 or SN2. The first step is a nucleophilic addition, followed by an SN1 type substitution. Okay. The last thing that we could see with our nucleophile, we could have the epoxide formation, which should also look really, really familiar. We can have the electrons from our double bond coming out and attacking that oxygen. Oxygen now has too many bonds. So what we're going to need to do is break some bonds. So we could go ahead and take the electrons over here and swing them towards our oxygen. Now that carbon has too many bonds, so we can send some electrons up to that oxygen. Okay. That oxygen is now negatively charged, so we can share those electrons with that hydrogen. These electrons can swing down, and we end up with a giant mess of arrows forming our epoxide. Okay. Some cases the giant mess of arrows is correct, some cases it's not. This is the only case where the giant mess of arrows is correct. Okay. What's that? You don't need to know the flow, you need to be able to, given the flow, tell me what you get. Yes?
So that the right structure there, that is MCPBA, right?
This structure in here is a peroxide. It is not technically MCPBA because the B in MCPBA stands for benzoic. I've got this generic with the R. So it is the equivalent of MCPBA, but it is not that species. Okay. Questions? Okay, we've got the alkene reduction and oxidation. I couldn't find a reduction one, but you all remember how to do your reduction? First we need our alkene. To reduce, what do we have to do? We need to add hydrogen. In the process of doing that, we get rid of the double bond. Okay, in this case, we'd end up with ethane. We did an addition reaction because we started with two species and we put them together into one. So that is still technically an addition, better referred to as a reduction. This reaction is very, very similar to the Br2 reaction, where the double bond could act as a nucleophile, except hydrogen's not polarizable enough to react immediately with the alkene. So we have to add in a catalyst. Our catalyst is typically, we can get palladium, platinum, nickel, any one of those. Okay. We could also do oxidation when it comes to our alkenes, and that's what's being shown below. That's the osmium tetroxide, which adds to the double bond and forms this goofy intermediate. That is then followed up with some kind of oxidizing agent, which will kick off the osmium portion, leaving behind the oxygens. And we end up with the diol. Okay? You're responsible for knowing that those reagents do that conversion. You're not responsible for knowing a mechanism. Hence, I'm not showing you a mechanism. Okay? Questions about your alkenes? Because I think that's the last of the alkenes. Yep. Chapter 7 was our alkyl halides. There's a lot of information crammed into Chapter 7. Okay? You get the nomenclature of your alkyl halides, which is probably the smallest portion of that information. Most of it is going to come down into the two main mechanistic types, substitution and elimination. Okay? As far as the synthesis or reactions of our alkyl halides, they're either being substitution or elimination. Okay? Those are our two primary mechanisms when we have those functional groups. So like I said, lots of information. It's probably going to be helpful to go back and review the last substitution or the last alkyl halide slideshow. What I tried to do was pull out the big ones. You need to know what we're looking at for our substitutions are our nucleophiles. There's a very large portion of those reactions. So you need to know what a nucleophile is. This went through and describes those individual pieces of what happens with your nucleophiles. You're responsible for knowing those first 3 rules. All the other rules you might see in future classes if you decide to take future classes. Okay? The other big portion of your alkyl halide reactivity, particularly with substitutions, is the leaving group. Something has to polarize that bond so that it can react. That group is going to take the electrons away. So we need to have something that takes them. That ends up being our leaving group. Okay? It's pretty much the inverse of a nucleophile. In general, the best leaving groups end up being weak bases. Okay? They have to take electrons, so it doesn't make sense to call them acids because they're leaving with electrons. And then as far as reactivity, we want them to be as stable as possible. So they'll end up being a base because they took the electrons with them. And we want them to be stable, so they need to be weak. Okay? In general, what they end up doing is stabilizing that charge as best as possible. The ways we can stabilize charge would be size. So the larger our group is, the larger the charged atom is, the more stable that negative charge is. What else? Electronegativity. The more electronegative it is, the more willing it's, or more able it is to grab the electrons and bring them with it. What else? Those are the two big ones. Yep, that was the first one. It's related to size. Thank you for your honesty. Comes back to stability, resonance. If we can perform resonance on that structure or show resonance, the electrons are being moved throughout that structure. Ultimately, what we're saying is that negative charge is now being spread over a larger area. Now, in this case, instead of it being on a single atom, it's over several atoms. Okay, so it's still ultimately a size argument. We just have to do some more arrow pushing to figure it out. Okay? Deciding between the SN1 and the SN2 mechanisms. Okay? This summary slide is helpful. You need to know these things. The primary things that I'm going to be concerned about would be looking at your substrates. Okay? So under SN1 conditions, we need a stable carbocation. Under SN2 conditions, we're looking for minimal steric hindrance. Okay? So knowing what big key features are going to really help out. You could decide that that's too much information or too vague. And you can go through and look at substrate structure, okay, and memorize them in that fashion. Your tertiary is going to stabilize the cation best, so that one's going to react the fastest. In an SN2 reaction, the methyl halide has the least amount of sterics because you're looking at hydrogens blocking the backside. Okay? The other effects that are up there, you're responsible for knowing your stereochemistry. And shoot. For sure you need to know, well, for sure, it's tied in with nucleophiles. So knowing that for an SN2 we need a strong nucleophile will be helpful as well. Okay? Solvent effects, probably not as important, but you should be familiar with what's happening in each of those cases. Ultimately, when it comes down to it, what we're looking at is how does that solvent affect the overall reaction. If we're in a polar protic solvent, if it's protic, we have a very positive hydrogen, which means we also have a negative conjugate base. That negative can go a long way towards interacting with, say, other positives, say like the carbocation, which was our primary concern in the SN1 reaction. So a polar protic solvent does a fantastic job of stabilizing that cation. If I can form the cation, my reaction can progress forwards. Okay? When we move to the SN2 mechanism, if we use that same solvent, that protic solvent, we have H+. H+ can go a long way towards stabilizing negatively charged species, like nucleophiles. For the SN2 reaction, what do I want my nucleophile to be? Strong, which means very negative. A protic solvent would do the complete opposite of making it negative, makes it more neutral. Okay, so a protic solvent is a bad choice in the SN2. That's why we move to a polar aprotic solvent. Okay, so recognizing why things are occurring, why things are favorable is pretty important to get you through this. Substitution and elimination. This kind of breaks down some of those individual pieces a little bit more. The strength of the nucleophile is really going to determine the order for your reaction. Okay? I didn't show the elimination sample slide, but your eliminations are very similar to your substitutions. If you have a strong nucleophile or a strong base, so something that's negatively charged, that's going to push the order for the reaction or the 2 type. Okay? So if you have a negative charge, you're looking for either the SN2 or the E2 eliminations. Okay? Some patterns on what things you could see between nucleophiles and bases, determining the difference between them. Okay? What mechanism is the nucleophile going to be important for? Your substitution, SN for nucleophile. Where's your base going to be important? For the elimination. So knowing the difference between those 2 species can take you into one result or another. Okay? Next piece you could look at is your substrate structure. Quickly, if you've got a primary halide, you're immediately jumping into the SN2 being the most likely mechanism. Okay? If you've got a secondary halide, you're going to hope something useful is happening in rule number 1. So going all the way back up here and saying, is there something useful there? If you don't have that help, that really sucks, because that means all mechanisms are possible. SN1, SN2, E1, E2. Okay? That secondary substrate has all sorts of possible reaction or mechanistic types associated with it. If we move to the tertiary halide, we get a mixture of your eliminations and your substitutions. Other things you can look for, high temperatures typically favor elimination reactions. Bulky bases also favor eliminations. The larger they are, the more likely they'll react with hydrogens and not interact with larger things, like electrophiles. Okay? Final summary of everything that's up there. So you can see all of those. You can go back through that and make sure you've got those memorized as far as which things pattern to which.
Or put on our sheet.
Or put it on your sheet, yes. Forgot about that. You do have that sheet.
Let's not forget about that. That's important.
Well, it doesn't affect me. Complications. Complications with each of these. Really, it's going to come down. Well, actually, yeah, these complications are important. You lose stereochemistry when you're looking at the SN1. You end up with a racemic mixture. The other problem with your SN1 mechanisms is they directly compete with your elimination, your E1 mechanisms. If you have an SN1 mechanism, you have an E1 product as well. Okay?
What's racemic mean again?
Racemic means a mixture of R and S.
50-50.
Exactly right.
They counter each other.
It is not optically active, yes. So,
See, we retain some stuff.
I know you retain some stuff.
We're learning.
SN2, inversion of stereochemistry. If you start with a certain chiral center, you'll end with the opposite when you go through the SN2 mechanism. With your elimination reactions, you're most commonly seeing the trans alkenes in both cases because those are the most stable. Your groups are as far away from each other as possible. You'll end up seeing Zeitz products, meaning the most stable double bond, which means the most substituted, the least amount of hydrogens on your double bond. Okay? The other issue is that they're simultaneous with your SN1. When it comes to E2, you can ignore the Hoffman products. You do get the cis possible products. Why is cis possible? Comes back to the stereochemistry of the E2. Okay? You have to be in that anti-alignment for the E2 elimination to occur. Questions? Oh my gosh. Halftime. Are we ready for a break? Should I keep talking? Good.